Thank you. Yeah, so to be clear, what you're going to see throughout this talk is a giant rainbow cake, which is very hard to miss. And anytime you see a giant rainbow cake, you can ask me any questions you like. But of course, anytime through the talk, if you're confused about a particular point, please raise your hand. I want to make sure everyone understands everything. And today I'm going to be talking about physical problem solving across timescales. And a lot of this work is going to be work that I did during my PhD. And we're going to focus mostly on humans here, but we'll have a little bit of machine learning and robots towards the end. So in particular, what I study is tool use and tool creation and physical problem solving in sort of all of its forms. And one reason I do that is because there are many different organisms on the planet that can solve physical problems. And solving physical problems is actually critical to survival, right? So for example, this is an anglerfish that is able to plan trajectories of spitting in order to catch prey in the sky. Or birds are excellent architects and they can build these nests in order to live in, right? These are different physical problems that are being solved. Octopuses can collect coconuts from the ocean floor and use them as shields in a portable home that they can take with them to many different areas. And crows are particularly adept tool users. Maybe some of you have seen these kinds of videos, but they can do things like reason about fluids by dropping in heavy objects here in order to get a piece of food that they initially cannot reach. Tools also appear across our human history, right? And we can go as humans beyond just using tools to actually making tools. And this was key in our anthropological development. We can do things like create stone knives to allow us to cut things that we can't do with just our knives, right? Or hammers to allow us to crush things that we couldn't do with just our fists. Across many generations, we've refined our tools to do completely amazing things. Like this example of an artificial lung, which was created by an expert tool creator, a biomedical engineer, and then manipulated by these expert tool users, these surgeons, in order to implant that artificial lung into a patient. But even if many of our tools are passed down through generations, the sort of spark of innovation to repurpose an object as a tool exists in all of us. So this is an example of a young boy who has a very important problem of getting this tasty out-of-reach Easter egg. And he has this very innovative idea to use this shovel to do so. Tries both ends of the shovel. He's extremely persistent despite making no actual progress towards his goal, right? But he tries a variety of different approaches here. And unfortunately, he is scooped by an agent that didn't even have to use a tool to achieve this. But this learning experience, will shape him for many years to come. So these kinds of physical problem-solving capabilities come very naturally to us as humans, but they're actually surprisingly difficult to replicate in machines. So the machine learning and robotics communities can be sort of split into two kinds of approaches that people try to solve physical problems. This is the pure learning approach, and this is an early example of what was considered a state-of-the-art model for being able to avoid obstacles in this way. Many of you might have seen this video before. And this took hundreds of thousands of years of experience in order to learn these policies. And they still fail in these extremely unintuitive ways. Now, if you want to say, OK, Kelsey, but that's 2017. We've moved on a lot since then. Here's an example from 2023. This is one of the largest VLMs being applied to this task of simply get the red objects to the cup. You'll see what it does. It kind of goes towards the red object, right? But as you see it play again, it does a lot of things that don't look quite like going towards the coffee cup, right? Like it moved that object away from the goal of the coffee cup before coming back. This is a highly inefficient policy for actually achieving this goal, right? And this is literally our best VLMs in 2023, trying to solve a task of just move all the red objects to the coffee cup. And this is, because it's a VLM trained on an internet's worth of experience. So very, very inefficient. So in order to gain efficiency, robotics is often focused instead on these much more structured models. And in these kinds of models, you basically bake in a lot of your world knowledge into your robots, like in this case, at the top here. And these can do really amazing different kinds of planning capabilities. They appear to actually solve the goal. But if you look carefully, the physics that they use to solve these is extremely unrealistic. So in this case, this is in simulation. And if you see this thing get moved onto the paper, that red ball, it's going to then rotate the paper in a way that would never happen. The ball would roll off of that immediately in order to solve the task. you can see that when these kinds of things are applied to the real world, like in this Boston Dynamics example, incorrect estimates of the physical parameters, because it's not learning enough from its environment, cause it to make potentially very catastrophically expensive failures. So in order to be more adaptive, people have turned to these learning models instead. Now, humans and animals seem to be striking a balance between these two extremes, right? We can learn new actions or new physics that we didn't previously know, but it doesn't take us hundreds of thousands of years of experience to do so, right? Sometimes it only takes us one or a few attempts to get the right idea. So my research is really about how people and machines can reason, plan, and learn in complex environments similar to these kinds of physical problem-solving tasks. And so a lot of my work goes into developing different environments in order to test different theories about what physical problem-solving requires, but then also to think about how to combine the best parts of these structured kinds of robotics methods with learning in order to get both adaptivity and efficiency. And the structures that I look at are those that we know are important from research in cognitive science, but which have been less well studied in the context of action. So for example, we believe the world is composed of objects, and we know that even very young infants have notions about what these are. These objects exist in relation to one another in the world, and this helps us draw analogies and similarities that allow us to transfer knowledge to different kinds of settings. And we also know that people use intuitive physics, which we saw a little bit of yesterday, in order to reason about their perception of the world. And we also think that this guides how they act. So in the talk today, I'm going to look at learning across multiple timescales of experience, across just a few examples within individual problems first, then how to generalize experience across related problems, but just from a few attempts, and then looking at how people actually learn across lifetimes in different kinds of bodies in order to solve different kinds of physical problems. And as promised, here's that large cake that you can take a look for throughout the talk. I'm going to assume no one has questions about the introduction at the moment, and we're going to jump into the very first project here, which is policy learning with a scoop of mental simulation for rapid problem solving. So in order to talk about this first project, I want to motivate it by showing you this perhaps surprising object. So has anyone seen a fork like this before? Okay, yeah, people who've seen me give this talk before. That's cheating. But what's cool about this, right, is that you can immediately perceive this as a fork, and yet you know immediately that if you try to use this fork like normal, it would fail because of this chain, right? It's essentially you're running a mental simulation in your mind of what would happen if you took a classic action to this object and tried to use it. And you could even potentially use that simulation to devise a better idea for how to use this fork, right? For example, you might try grabbing it just above the tines here instead of interacting with that chain, and that's going to be a less pleasant eating experience, but it is going to work. So this project was looking at the development of a game in order to try to capture some of that reasoning behavior. This game is called the Virtual Tools game, and in it, your goal is simply to get the red object into the green area by picking one of these tools and clicking on it, and then clicking somewhere in the scene in order to release it. Now the trick, and why this is hard, is that you only get one action to try to solve the goal. And if you're unsuccessful, you have to reset the world and try again. So this is someone playing this catapult level, where they start by just trying to hit the ball directly towards the goal. And when that is unsuccessful, they switch to this catapulting strategy. Now, in the theme of what makes this a sort of high-dimensional task, it might seem very simple, but actually relative to previous work in model-based reinforcement learning, which is where this game sort of lies, the kinds of things that people look at in how people take actions look like these decision trees here, where you assume that you give people basically a current state, and then they can take maybe one of two actions, go left or go right, and that's going to put them into these other two somewhat arbitrary states. And again, from each of those, they can choose to go left or right until they eventually reach some reward. But this is a very low-dimensional action problem, right? You only have two discrete actions to choose from and a very small number of different states that you can reach from that. Whereas this tools game actually has a reasonably high dimensional action space in that you have to select a tool, and then you could place it literally anywhere in the scene in order to try to accomplish your goal. It also has very realistic dynamics that are done by intuitive physics, as opposed to the arbitrary kinds of dynamics that people have previously studied in model-based reinforcement learning. And it has this sort of rich dynamics feedback versus just having a scalar reward. So here you get to see the actual outcome of your action, potentially updating something like your physical parameters before acting again, instead of just having a reward signal. So we didn't just look at this catapulting example, right? We created a bunch of different levels to test many different physical concepts in action here. So from things where you have to creatively think about how to hit a ball into a goal without actually hitting it directly, like in this catapulting level, to others which require you to support something, support a platform so that it doesn't fall, so that a ball can roll top into the goal, or other things like unhinging, like in this unbox example on the upper right. We also created what we call these adversarial level pairs here, like shafts A and shafts B, where the only difference between these is that in one case, one of the possible two solutions is blocked by this blocker. And what we wanted to know was whether or not people are actually sensitive to these very small changes in the scene that have big implications for the physics of how they can solve it. So what's really fun about this game is to actually just look at the kinds of things that people do. So I want to show you two examples of that. This is someone playing this table level that I mentioned to you a moment ago. And the first thing they try is very classic, which is just take the largest tool and hit the object as much as you can. And then they try an even more classic thing, which is to try exactly the same failure again. But then they think about this a little bit more, and they realize that they could place something underneath the platform in order to support it, and then simply have to fine-tune that action in order to be successful. On the right, this is a participant playing what I affectionately call the PhD level, in that it's very, very challenging, but once you are successful, it's very rewarding. And here, the trick is that you need to hit this ball, right? And they do manage to hit the ball, but well, we might hope it's going to go into the goal. It doesn't quite. So the question is, how can we hit that ball with more force? So you want to try the larger object. Maybe this weird one will do something. Nope, that doesn't work. And then an interesting thing happens where when they put it above this platform, it rotates in a way that allows them to get enough momentum onto that ball so that it goes into the goal. And I show you these examples just to show that humans in this game are demonstrating these sort of aha moments of insight, right? Where they have finally the right idea about the kind of thing that they can do. But they're also not guessing randomly. They're taking these structured, object-oriented kinds of attempts and then using trial and error learning in order to refine those solutions to actually solve the task. So to understand the sort of cognitive ingredients of what's going on in people's mind for this, we built this model called the sample simulate update model. And I want to walk you through this in a little bit of detail because it's going to come up in a few different places. It's actually a very simple model, but it's critical in that it narrows down the action space by taking these object-oriented initial attempts. So everything you see here in orange represents the probability distribution for the kinds of actions that the model is even going to consider taking. Concretely, what it does is it just selects randomly a dynamic object in the scene and then selects an offset to that object that's centered around it such that when you drop something and physics is turned on, you're going to have an interaction with that dynamic object. From that sample, the model then runs simulations in its mind. These are noisy simulations, so we add some amount of noise to the collisions as well as uncertainty about the mass and the elasticity of the objects. So what you can see here are multiple simulations unfolding for one given action that's being simulated, which is to drop that large object. And then if that simulation looks to be successful, if the majority of these simulations from this particular action go into the goal, then you're going to try that action in the real world. If not, you're going to update your beliefs based on your simulations of what actions are likely to be successful and continue this process back and forth here for a maximum of, say, 5 times. And then you're just going to try the best thing you've seen so far. So this allows you to get information from both actions and simulation to update your beliefs about what kinds of actions are good to take here. And we're going to compare this simple model to humans to see whether or not each of these components, this sort of object-oriented narrowing of the action space, this noisy simulation procedure, and this policy updating mechanism are required to explain people's behavior in this task. So what we can do is first look at a very coarse level, which is to compare the model attempts on the x-axis to the human attempts here on the y-axis, with each individual point here representing one of the different levels. And what we see is that across the 20 levels, we get a pretty nice correlation between the model attempts and the human attempts, suggesting that at least at a coarse level, the model is roughly capturing how difficult people find each of the different levels in the game. You can do the same thing with accuracy. So this accuracy number for humans means people did eventually just give up after 2 minutes. And so in this case of, for example, table B, only about 30% of participants actually solved the level at all. And we can look at the same thing for the model that's shown on the x-axis. And again, we get a pretty nice correlation between model and human accuracy in this game. But we can look in even more detail at a human model comparison here, where instead of just looking at overall attempts and overall accuracy, we can look at these cumulative solution rates, which is the number of participants who solved each of these levels in a given number of attempts. So for example, in this basic level here, after a single attempt, both the humans in black and the model in red were about 50% solving it. And by about 4 attempts here, almost 100% of humans and 100% of model runs solved the basic level. And across a lot of these different levels, the red line and black line are pretty well matched, suggesting that the model is capturing well the rate of solution for each of these different problems and not just the overall numbers. And we can actually look in even more detail now. And now we can actually look at the particular placements used by humans and the model. And we'll look at 3 cases where they agree, but 1 case where the model is actually significantly outperforming humans here to see what's going on with that. So visualized here are the first and last placements for both humans and our model, where each of the little colored dots is an individual participant, with the color being the tool that they chose and the position being where they placed that tool in the scene. And the model is shown as these sort of blobby background estimates, also with color-coded by the tool chosen. So if we look at the first placements here, let's take a look at this catapult level. Both humans and the model seem to be trying 2 different kinds of actions initially, right? They either try to hit the ball with the small triangle object, or they try to catapult the ball into the goal using one of the 3 available tools. But by the last placement, both humans and the model have converged on trying to catapult the ball into the goal using the largest available object. And this pattern looks sort of similar for at least 3 of the 4 levels that I'm showing you here. But what's really interesting is to look at this last level, which is falling A. This was the one that the model was significantly outperforming humans. Now, this level can be solved in one of 2 ways. You can either place an object above this container, such that when the container starts to fall, the object is going to tip it over. The tool object is going to tip it over from above. Or you could do a much simpler thing of placing any object beneath the container to destabilize it. So when it falls, it's going to become destabilized, kind of like putting a banana peel under someone's foot. So in humans, people are particularly biased to try to drop something from above the container in order to flip it over. And they actually struggle to find this solution that's much easier to accomplish in this task of placing something beneath the container in order to destabilize it. Even though if you notice, they were totally happy to put something beneath the object here. So it's something contextual and specific to something like containers or destabilizing an object that people are finding really difficult here that the model sees very easily because it's just sampling, again, this object and an offset to it in order to interact with the scene. So humans seem to be biased in these sort of interesting contextual ways that we haven't accounted for so far in this model. People are also remember I hinted that we would have these levels with these very minimal comparison differences. People are extremely sensitive to that. So if you look at this shafts A example, most people decide to use the large pink object in order to get this red ball into the goal because it's a little bit easier to do so. Whereas in this shafts B case, they switch to an object that's going to be able to fall through the shafts and hit this one on the left, even though that's a little more tricky. And the model similarly switches between these, just like people do. We can also compare to various ablations of this model by removing either the simulation, the updating mechanism, or the prior from the full model. Or we can do something like tune the simulator by updating the beliefs based on our observations of the outcomes rather than updating our policy. And we can even learn the prior by just taking a huge number of randomly generated levels here and applying our favorite deep reinforcement learning algorithm, in this case DQN, to try to learn a policy across all of these that's going to suggest a single action that should work correctly. But if we look at how each of these models compares to the full model in terms of how well it captures human accuracy, our full model gets a much nicer correlation than all of the alternatives. And this DQN that's trained on a massive amount of background levels actually performs extremely poorly here, often getting less than 25% of the model runs here being successful for a large number of the levels. To just give you a little bit of intuition for how these different ablations perform, we can look at two of the different levels here, bridge and catapult. In this bridge level, you have to place something beneath these two platforms in order to stabilize them so that the ball is going to roll off and into the goal. And this is a problem mostly of having this sort of aha insight, as well as having good priors for the kinds of actions you're going to try initially. And so what we see in this bridge model is that the models that do not do particularly well are the ones without the prior here. So this brown line is getting a much worse score relative to humans relative to the full model in red, as well as the humans in blue, even though we don't actually need simulation or updating to the same extent. In this catapult level, this actually requires updating because people need to fine-tune the amount of force that they're applying to this catapult lever arm. And so here, the model that doesn't have updating, which is this one in orange, performs much worse than humans and the full model. So that's just reassuring. It means that the different components are able to explain human performance in the ways that we would expect across the levels where we think those components are necessary. So overall, we think that this project and this model supports our sort of allowed us to understand how people not just use physics to infer things about the perceptual world, but also to act. We found that learning within these kinds of problems was supported by these object-oriented action priors to narrow down the search space of all things you might consider to just ones that are likely to have an impact on the scene. We needed this noisy physical simulation in order to act efficiently, as well as this rapid policy learning based on failures. So now there's a cake. Does anyone have a question about that first section? Yes?
So in your model, how do you specify the prior for the action space? Is it uniform or?
Yeah, so it's technically a mixture of Gaussians where each mixture component is a dynamic object in the scene. So it's sampling a dynamic object in the scene and then sampling an offset to that, and that's what the prior is representing.
So in the case that you show the models substantially outperform the humans, if you plug in the prior infer from the humans, would you be able to narrow the gap a little bit?
Yeah, that's a great idea. So we haven't actually tried to fit a prior to the human data and then use that in the model. But I would expect that if we did that on a level-by-level basis, we would be able to capture the human results a little bit better. What's confusing is the fact that in that falling level, they had a very different prior from what we saw in like the table or bridge levels, for example. And so we'd like to understand sort of what the generative mechanism to get to that prior is from human experience. But I think you're absolutely right. Yeah. Yes.
I think I'm not entirely understanding the model. I saw the box and arrow version, but is there anywhere that you have the equations or something so it can be a little more?
Yeah, I can go through the paper, but it really is a very simple model where it have a mixture of Gaussians prior. We run noisy mental simulation by sampling multiple outcomes from a given action conditioned on having a little bit of noise in the mass as well as the collision dynamics. So we get, yeah, just random sampling, yeah. And then for each of those simulation trajectories, we calculate the minimum distance to the goal that it achieved. And if that number averaged across those trajectories is better than a given threshold, we act. And if not, we just do like a reinforce update of the policy distribution based on those outcomes. And that's it. There's nothing fancier. Nope, only the final goal. No sub-goals. Yeah. Okay. So in this next section, we're going to talk about more abstract learning over slightly longer timescales. And to motivate that, I want you to just think about this is the kind of learning that we actually normally experience when we're learning how to use tools, right? You learn how to use a whisk, and you don't just learn how to use that whisk for this particular batter, right? You learn how to use a whisk in general that can apply to many different batters. And you learn how to apply more force to things that are perhaps more viscous, for example. Or a hammer, you learn how to use it for a variety of different objects you might apply it to. Or, learning how to use a catapult, which I'm going to show a couple more examples on this next slide. So if you haven't figured out from the first part already, I do really like catapults. I think they're very cool. And in particular, it's because of sort of how versatile they've been used across human history, right? So in very early human history, catapults were used to, hurl a very large object, maybe it's on fire, at your enemy's castle. But more recently, they've been used to actually launch people into a lake. Or in even more recent times, if you're stuck in quarantine, you could make a catapult out of just everyday things you find in your house, like a spatula, a crumpled piece of paper, and a toilet paper roll, right? And what I think is really interesting about these cases is why do we call all of these a catapult, right? It's because they have certain relational similarities between these objects. This catapult thing showed up in our game too. And the reason that we call all of these catapults is because, for example, they have something that you're launching, right? A piece of paper, a human, or a large rock. And they have a lever arm of some kind and some way of applying force to the end of that lever arm in order to launch that object into some new location. So these are sort of relational symbolic concepts that can be reused in new situations in order to allow us to not have to plan again or search again totally from scratch, but instead to reuse what we've learned again in the future. What we wanted to ask in this project was whether people could sort of rapidly learn these kinds of abstract relational strategies which can support generalization to new problems. And if so, can we predict how and when people will generalize this knowledge? So this catapult case, for example, we might want to be able to generalize our experience here to either new kinds of tools, but a very similar kind of setup, or even to a very different scenario here where you need to catapult this ball so that it hits this other one into the goal here. If you look sort of earlier in cognitive science, we already know that people can use relational and functional structure to make inferences about new percepts. So this is some very famous work by Medine, Goldstone, and Gentner on what it means for two objects to be similar to one another, suggesting that people take into account relational information to do so, or these very famous Bongard problems. And even very young children can make inferences about which tools are functional to use based on relational similarity of those tools rather than sort of just the textual specifics. So if you needed to get something that was out of reach and you first had experience with these tools, do you generalize this hook to a hook that looks different texturally or to an object that looks texturally the same but functionally distinct? But what we want to know in this project is not just if you see these kinds of relations, can you group them together in meaningful ways, but how could you actually learn the sort of relational and functional structure via just limited trial and error experience? So not by perceiving, but instead by acting. And so we set up a pretty similar task to the one that we just saw. But here, instead of people playing only one level, they're going to play 10 related levels, where these levels all come from the same sort of concept type. So for example, in these catapulting ones, They're all catapulting concepts, but the position, the size, the height of the catapult differs in all cases here, as well as all of the available tools changing, and similar with these tipping examples or these table examples. What we're then going to test is whether people generalize to these near transfer conditions, where you have levels that look very similar to the ones seen in training, but are a little bit different, or these far transfer conditions. And the far transfer conditions here, again, use the same physical concept. But for example, in this bridge level, instead of supporting only one object, you now have to support two simultaneously. Or in this tipping level, instead of tipping over the container, you need to tip this ramp such that the ball is going to roll out and into the goal on the left. The other critical thing about this experimental paradigm that differs from the one we just saw is that in this learning condition, people cannot play as much as they want. They only get 3 attempts in order to solve the goal. And so they have to use those limited 3 attempts across multiple levels in order to come up with a sort of relational, reusable strategy. So the first thing we can look at is just how do people actually do across the 10 different levels that they get during training. And in all 3 of our different conditions, catapult, table, and tipping, they do improve. They improve quite rapidly. So by about the 7th trial on average, people have already reached ceiling performance here. And if you look at then their behavior in the testing levels, people who are trained on the particular concept are shown in blue, and then people who are untrained are shown in red. And so for the near and far transfer conditions in table here, the people who are trained are massively outperforming the people who are untrained for those test levels. And similar for this far transfer case in the catapult. But what's sort of striking is that there actually isn't a difference between trained and untrained participants for these other 3 examples. And you should be surprised by this because people were learning very well the strategy from the training phase. So why are they not performing better in these test levels? We can take a look at that by looking at the actual placements that people use to solve these. So this is the catapult near transfer condition. And this is the catapult test level that I'm showing you here, with the dots being all of the different participants. Now, what's critical to notice in this particular test level is that there are actually 2 ways of solving this particular catapulting level. You can either catapult the ball into the goal, like we saw before, but because this platform is so raised up relative to the container, you can also just hit this ball directly. And people who were untrained in the catapulting condition saw this, and this is actually easier in this case to be successful. And so there was not an advantage of people who were trained because the catapulting strategy here wasn't actually the most successful strategy to use. But people were extremely narrowed in the kinds of things they could think of based on having experienced many successful iterations in the past. So I point this out to show that learning these strategies is actually not always helpful. Sometimes it narrows you into the wrong part of the search space. A sort of similar story can be told for these tipping cases, where here people actually individually separated themselves into those that discovered in training a strategy that was tipping from below. And I mentioned this is a little bit easier to be successful. But some participants also found extremely precise ways of tipping from above in order to be successful. However, this is actually just a much more difficult strategy to use. And if you look at people who are, again, untrained in this condition, they're much more likely to play something below. What's cool here, though, is that individuals who discovered a tipping strategy from below, for example, were more likely to use that still in these far transfer conditions. And similarly, people who discovered tipping from above were, again, more likely to generalize that to the far transfer conditions. So people sort of individually discover and then stick to these kinds of relational strategies that they learn. So now I want to talk briefly about how could we actually model this kind of narrowing behavior, right? From our full sample simulate update model here, what we think is going on is that people are basically replacing this prior or learning a new prior over related experience that's going to be like a relational strategy that's learned across previous levels. Now, the challenge is how can we represent this relational strategy in a way that generalizes across all these different kinds of tools, all these different absolute positions of the objects, and even across these sort of far transfer conditions where the concept is the same, but the scene otherwise has a different number of objects and looks quite different. So the way that we do that is by using this probabilistic grammar that I'm showing here on the right, and I won't go into the details of this just for time, but the central idea is that what we can do is we can learn a program to describe a relational strategy from our successes and failures. And this program, because it's represented in this relational language, is going to be able to generalize in ways that just updating an absolute position for each of the different tools is not. Now, this full model of learning these relational programs across levels and then using simulation within levels in order to find solutions makes a couple of predictions for what human behavior should look like in these tasks. One is that we sort of should be able to learn strategies rapidly from few attempts because you'll learn a program actually after only one interaction. These relational symbolic strategies should generalize to new problems, and they're going to specifically narrow the search space because they're replacing this prior with what the strategy thinks are going to be the successful actions. And this could be for better or for worse. If this is being correctly applied to a new problem, that's going to be good. And if it's going to be incorrectly applied to a new problem, then it's going to cause you to narrow down your search space in an inappropriate way. So we gave this model, the sample simulate update plus the relational rule learning model, access to exactly the same levels that people saw, but it doesn't get any of the human data. It just has to play the same levels in the same order as our human participants. And the kinds of strategies it learns in program language are something like this. So what this means in English, this first rule is saying interact with the dynamic object beneath the ball, which in this case is the lever arm. Find a location above and opposite the ball, which is this area over to the right here, and place a large tool there in order to have enough momentum. If we apply this model, if we apply this strategy in combination with the rest of the sample simulate update procedure, these are the actions that this model then takes. So you can see that in the majority of cases here, it's correctly applying this strategy, and the strategy is correctly saying to place a large object above this catapult lever arm in order to catapult the ball into the goal. And this looks very similar to the kinds of actions that trained people take on these levels. We can look at a couple of other examples here for the far transfer conditions. In this case of learning from these different support levels, the model finds a strategy that says pick the tool that is at least the container height, place it to the right of the table, and place it below the table. And again, what you're seeing on the left here is human participants, and on the right is the trained model. And you get a sort of similarly nice distribution for these tipping levels, where here we also see that the model, just like people, separates into learning these two distinct strategies, either placing something below the object on the bottom here, or placing something above the object in the top there. And only in placing above the object do we see that it actually cares at all about information about the tool. Because if you're placing something above the object, it needs to be very heavy to have enough momentum. So you need to select a large tool. If you're placing it below, it doesn't matter. So it doesn't have anything to say about that. If you look at how this compares on the test generalization conditions over all of the different testing environments, we see that these relational symbolic strategies help the model perform better for exactly the same levels that we see in people. And it causes them to perform worse or the same in the same levels that people failed on as well. So it's doing a nice job at capturing this sort of weird pattern of results that we saw in humans. So as a quick summary of this, we found that people learn these sort of abstract strategies via trial and error experience that they can apply to new tasks to narrow their search spaces. And then this can be modeled as this relational symbolic rule learning that guides mental simulation. So now we're at a cake. Does anyone have a quick question about that last section? Yes.
That model is very interesting. If you take, I mean, presumably in the first study, some kind of relational learning is also ongoing. So if just try this version, not worrying about transfer, but just looking at maybe the learning curve or the overall accuracy.
Yeah, so it's a great point. So one thing that's very different about the first experiment from the second one is that all the levels in the first experiment are in theory designed to be independent of each other. So we hope people are not generalizing. And in fact, if you look at the learning curves in the first experiment, people don't get better between the end and the beginning. They take just as many attempts at the end as they take at the beginning of the whole experiment. So it seems like they're not actually learning something in the first experiment, whereas we saw learning curves very strongly in the second. But I agree, it would be interesting to see if the model is like also in some sense correctly learning to not overgeneralize the strategies, because people in the first experiment don't overgeneralize them. That's what we would hope to see.
I was just curious, like if you treat IID, those
Yes.
Things, and apply the model in that way, even do you get kind of similar sorts of learning curves or whatnot?
We do. So we did try that modeling experiment, I suppose. And what actually ends up happening is that it just doesn't learn a prior at all, and then defaults to the object-oriented one, because the way that the program learning works, it's trying to basically find a program that's able to separate successful from unsuccessful actions. And when the levels are totally unrelated, such a program is impossible to find. And so then it just defaults to the object-oriented prior. So it should capture what we just saw. But yeah, it would be nice to have a concrete plot showing that. Yes?
How did you verify the validity of the programs? Are they grounded in the physics engine, or was there like an interpreter that you implemented?
So we implemented our own domain-specific language for the programs here, and I actually think that this grammar is probably insufficient to capture the kinds of relational concepts that people actually learn in this game. The grounding is with respect to the scene. So it's like based on the initial scene as input, it has all the information about the objects in that scene, for example, that's then going into the program learning, but it's not taking into account any of the dynamics. So the programs are not based on learning something about the trajectory of the objects. It's just something about the initial scene. But yeah, it would be cool to look at. Yeah.
So it's assumed that your model already has those. I see. So it's not really fair to the other models that are learning from zero, right? In comparison.
Yeah. So I mean, we didn't even compare it to a model that was learning from zero. What we compared it to was a model that was just essentially taking, in the original model I showed, right, you have this updating mechanism for updating the prior based on your experience within the level. And you could imagine just taking that prior and using it to initialize your next level. And that's what this is. So this is just based on object locations, but doesn't have any of the relational abstraction. But it needs still the object location. So it's actually using exactly the same amount of information.
Any idea why training hurts this particular model? A lot of the times the untrained is doing better.
Yeah, so in this particular case, the untrained here is doing better specifically in this far transfer condition for the most part, and this catapult one maybe a little bit. And I think that this is because in the far transfer condition, let me try to go back so you can see. This is this level here. And this is an easy one to solve if you place anything beneath this. And so the just default prior here is actually the most successful one. Yeah. OK. Great. So in this next section, we're going to talk about what actually happens instead of within a single experiment, perfect, across a lifetime of experience. And in particular, one complaint you could have had with all the work I showed you so far is that we are studying physical problem solving, but it's not really in the physical world. And actually, most of our experience of the physical world happens through our bodies by interacting with objects in the real 3D space. And so what we're looking at in this project is does different real-world experience across a lifetime actually affect the ways that people come to these virtual physical problem-solving tasks? And in order to answer that question, what we did was we partnered with some folks in the UK who study folks that are born with limb differences. What I mean by that is people who are born with either one or no arms, relative to people that were born with two. And we had the extremely good fortune to look at both children and adults in this setting. So we looked at both children and adults with and without limb differences. Now, asking this question of how does different real-world experience affect strategies for physical reasoning, previously, in order to study this, your sort of natural inclination would be to look at an actual physical manipulation tasks, right? But in this case, because these people have different bodies, their capacities for action in the physical world are simply different, right? One group has 2 hands and one group has 1 or less. So instead, what we did was we used this virtual physical problem-solving task where the capacities for action between these 2 groups are equal, because both groups can use a mouse approximately equally well. And so what we're able to look at is just this sort of abstracted physical problem solving, how that is affected by real-world embodied experience. So what we did first was we actually checked that the action space for these 2 groups has been equalized by just having them do a cursor control task where they have to click on a star in the center, then click on a colored dot in the periphery, a star in the center, another colored dot in the periphery, and do this 20 times total. And what we can then look at is the median motor error here on the y-axis relative to the age in years on the x-axis across our different participant groups. And what we see is that while children are a lot worse than adults and they get better as they age, there's no difference between the people born with 1 hand and 2 hands statistically in terms of the median motor error on this task in either the children or the adults. You can also look at the median motor reaction time here. And here there is a slight difference where adults with 2 hands are slightly slower, actually, in this task relative to adults with only 1 hand. But again, the difference is pretty minor here, and there's no difference in the kids. So we're reasonably confident that both groups can use a cursor approximately equally well, and so their action space should be equalized for this task. What we can then look at is just how they play now the real game, the virtual tools levels. And the first results we found were actually that there's basically no difference between these groups. So this is just looking at the percentage of the levels solved, the accuracy, for both folks with and without limb differences in the children and adults. And we do see an effect of age, where children get better as they age, all the way from 5 to 11 years. And adults, unfortunately, do get worse, starting at about 25. So I'm past that peak now, as many of us are, unfortunately. But you know, it's not such a decline, so there's hope. But what we found was that even though the sort of overall performance was similar, the ways that these different groups arrived at solutions actually differed quite a bit. And in particular, individuals with limb differences, and especially adults, took fewer attempts in the actual game in order to succeed. So actual placements of objects in the world in order to succeed. But they took more time, measured in seconds, for each attempt. So what we think this suggests is that people with limb differences are learning to rely more on thinking for physical planning, and this may be learned at an early age. Potentially because action, if you have only 1 hand, can be costly. If you get it wrong, it's harder to reset the environment, although we don't know. Just in the spirit of a high-dimensional plot here, we did also try to look at ways of analyzing the particular actions taken by these different groups. And so this is what you're seeing here are just clusters plotted over top the actual first actions of each of our different groups here. But we didn't find meaningful differences between them. So there's sort of some tantalizing stuff that suggests that maybe the adults born with limb differences here, the one-handed adults, are finding this balancing level a little bit easier to accomplish, but it's kind of hard to say. The only result we did find in this is that children, relative to adults, are much more likely to place tools closer to objects in the y dimension only. So they seem to be acting closer to the objects. And that is a statistically robust finding across our levels. Unclear why, but intriguing. So I've sort of taken you on this journey of these cakes. Do I have a couple extra minutes because I've taken questions throughout? Okay, sounds good. Does anyone have questions about that last section? I only have like 2 more slides, and then maybe we can ask questions about everything. So that sort of concludes all of the cognitive science stuff that I want to show you today. And I wanted to just show you a very small snippet of some of the stuff that I've been doing at DeepMind with, instead of looking at how humans solve physical problems, trying to understand how machines can be made to solve problems as well, and hinting at some sort of challenges for future cognitive science work. So I'm going to talk to you briefly now about making new measuring cups with differentiable physics. And this is motivated by going a step beyond using tools, which is what I've talked to you about so far today, and going towards creating tools. So creating tools can range from like these sort of phone games like Happy Glass, where you have to draw an object in order to reroute this fluid into this container. It can be extremely large-scale agriculture projects like creating rivers in order to irrigate fields. And it can also be extremely precise engineering, like being able to design an airplane that's going to have maximal lift but minimum drag in order to transport us across the globe. Now, we designed some different environments to try to understand the sort of tool creation process, ranging again from sort of this sort of everyday behavior, like being able to create tools in order to put fluids in particular different places, to this sort of very high dimensional action space where here you have to design the height field of this landscape in order to reroute these particles into these different pools, to things that require like sub-millimeter precision, like this airfoil design. In all these cases, what we want to do is create a new object in order to solve a task better than sort of the default thing that you would try. Now, if you try to do this particular challenge with this sample simulate update model, you would fail completely for the reason that this action space that we considered initially, while I claimed it was higher dimensional, it's still not that high dimensional, right? You picked a tool and you placed it somewhere. But in this landscape creation task, you have to choose the height of each one of these different points within this landscape. That's a 625 dimensional action space now. And that's totally intractable to just sample random landscapes, simulate them, and then see what happens. It's just totally intractable to do this. So what we did instead was we said, OK, what if we think about an alternative way of representing the simulator that would allow us to somehow search through the space better? So what we did was we replaced the simulator, instead of just a noisy simulation engine, we replaced it by a graph neural network. I'm not going to go into any of the details of how graph neural networks work, but the key properties of graph neural networks that are going to enable us to use them for tool creation are that, first of all, because they're neural networks, they're differentiable. And this is critical because it allows you to pass gradients through the graph neural network in order to update all of your action dimensions simultaneously, instead of having to just use a reinforcement learning method. The other key things about graph neural networks are that they generalize across many different physical scenarios. So for example, you can train them to predict physics in this very small domain with only a blob of water and a single tool here. And then they can generalize to these crazy like fluid scenes with many, many particles interacting with many, many different ramps. Well, we then use these graph neural networks in combination with differentiable optimization to then design tools that allow us to reroute these fluid particles in many different ways. So these are 3 examples here where we start with just some random initialization of the black line here. And then through optimization with the graph neural networks, we're able to create containers and ramps and funnels just from a reward signal of trying to get the blue fluid into the yellow region here. You can also design new airplane wings about 40 times faster than the leading engineering solvers. And you can do these landscape design tasks where if you compare using these gradients through graph neural networks to doing the same thing we did with the sample simulate update model on the right here, you can actually solve these tasks where the sampling-based procedure simply cannot. And there's a lot of cool work to look at sort of how these graph networks compare to human representations of physics. How can we use these insights to maybe understand how people not just use tools, but design them, and how people actually refine their designs? Do they use gradients? Do they just resample again from the prior? What exactly do they do? All right, I'm going to skip through. Well, I'll just end on this slide, actually. Yeah, so I talked to you today about a few different timescales, right? Learning within problems, learning across problems, and learning across lifetimes. But there's still quite a lot of cool work to do in extending these timescales to development, generations, and evolution, and hopefully eventually to reach the ability to design things like artificial lungs. Thanks very much.